Greetings, chemists. Today we will be talking about atomic structure, and we will be building off the ideas that you learned last year in physical science. Now, I understand that I don't have the voice of Neil deGrasse Tyson or Morgan Freeman, but I'm going to take you on a little tour from kind of the size scale that you're familiar with on an everyday life to the unimaginably small, looking at the atom and below. So there is a link that if you want you can explore on your own, but otherwise I will show you part of it now. Let's just resize that. Before we proceed to talk about the different models of the atom, hopefully you can remember there hasn't just been one. This has not been a static process. The model has evolved over time. So hopefully you can remember a couple of these scientists and some of their contributions to the model of the atom, and maybe some of the experiments that led to their findings. So try to think back a year. Do you remember who the person is all the way to the left? Well, either way, we'll go forward and talk just a little bit about each person and why they are significant. Before we talk about the modern day atom, we did have some early philosophers who came up with some pretty cool ideas themselves. One of them is Empedocles, and about 2,500 years ago, he came up with the idea that everything on Earth could be described with four elements: fire, earth, air, and water. And so, and they come in different proportions. So, like a rabbit who's warm, that's the fire, and who's solid, that's part of the earth, and the water. If you cut open a rabbit, there's liquid inside, and the air they breathe. That you can see the stomach go in and out. Or a rock might only have a couple proportions of those. And I think it's a really cool idea, and it was some of the foundation to what we now know of as modern elements. If you are interested in this idea, you can play the game Little Alchemy, and there's a couple versions online, and it lets you build things with these four different elements. So it's a pretty fun game. I would check it out. So now begins the line of philosophers and scientists who've then taken the idea of the person before them and built on them or disagreed. And so now we have Democritus, who said, no, each individual substance, like a tree, or in my crude diagram, a woolly mammoth, is made up of smaller things. And if you kept cutting them in half and in half and in half and in half, you'd eventually get to something you couldn't cut. Atomos, he called it. And that indivisible thing that you couldn't cut would be that atom. So that woolly mammoth is made up of a woolly mammoth atom, and he was made up of Democritus's atom. There was then a big period of history where nothing really changed, and there wasn't any breakthroughs in this idea of an atom until around the 1800s, where some mathematicians started putting together some ideas of how molecules moved. And here are the people you should be familiar with from last year and some of their accomplishments. So one of the things I want you to do right now is to pause this video and just reread through some of this and try to remember some of their key ideas. So pause the video now, and I'll highlight a couple of them right after this. Great, so hopefully you paused it, and here we have the 5 models of the modern day atom, and below the plus signifies like some of the significance that their model had, and the minus is some of the limitations that the model had and what it did not accomplish. So you have Dalton, who has kind of that billiard ball model, a solid sphere, and an atom is neutral, he knew, and it was solid. Thomson then built on that idea when he discovered the electron, and so how there's something smaller than the atom. It's an electron, and it's negatively charged. And his model was called the plum pudding model because overall it was positive, but it had some dots of little negatives throughout it, making it still overall neutral. Ernest Rutherford, somewhat accidentally, discovered the nucleus, that a positive center that takes up almost all of the mass of the atom is right in the middle, and it's positive. And so most of the atoms is empty space, and that was one of the big accomplishments Rutherford had, that he knew that an atom is mostly empty space with a positive center. He essentially directly discovered the protons, but he did not name them the protons himself. But there were some issues with that as well, and he can't explain how those electrons don't just collapse into the center. And so Bohr tried to later describe it with what we call the planetary model, that the electrons orbit around the planet, or orbit around the nucleus like planets orbit around the sun. But he still had some other problems as well. And we use his Bohr model to now teach about the atom because it's very intuitive and we can really understand it, and it's a lot easier to understand than now the quantum model, which we're going to get into in later slides. So the Bohr model has its limitations. It's not perfectly correct, but it does give us a good teaching tool to teach about all of the different ideas. And so we'll talk about light, because light is one of those phenomena that we need these more evolved models to describe. So we'll get into the quantum model and all of the craziness that the quantum model encompasses. So in the early 1900s, Bohr's model stated this, that the electrons orbit around the nucleus, so they're in motion, and they exist in discrete orbits. So these electrons can't be between those blue lines. They have to either exist on the line or on the next line. They can't go in between. And so when something gets energized, then the electrons are going to jump, and in turn, as they jump, they emit light in the process. They emit energy in the form of light. So I will draw, for instance, some red, maybe illustrating some kind of heat, and that heat comes in and hits an electron, and that electron then gets excited. So that electron jumps from this first energy level up to that second energy, or the third energy level, because it's excited. It could jump to the second, the third, or fourth. And then as it jumps back down, okay, so it stays there for just a brief time, but as it jumps back down to that original spot, in the process, it emits its own characteristic energy in the form of light. So this is kind of released, and this is energy absorbed. So we'll talk a little bit more about this idea. So without going into the math, and there's some math behind how much energy is released and absorbed, The electrons essentially can jump from the different levels, and we name the levels n equals 1, the closest to the nucleus, and so forth, n equals 2 and 3. And so the idea is the bigger the jump from maybe level 1 to 3 or 2 to 5, the more energy was absorbed, and thus the more energy is going to be emitted. And energy is directly related to the frequency and the wavelength of the light. And so the color of the light that is emitted is going to depend on how big of a jump they had. So we'll learn that more in the second lesson. So the math gets really complicated with this, and we're not going to go into it, but you can see you can't find any of the electrons in this picture, but you can show the regions where they're more likely going to be found. And so there you can see kind of two clouds around this nucleus, and these clouds actually take up some fun, complicated shapes. But at any given time, there are going to be electrons in these regions, and of course those electrons are still moving all about. That was a little refresher into the people who have led to this amazing model of an atom that we currently have. And before we move on, I want to say this quote from Isaac Newton. And he said, "The only reason I've seen farther is because I've stood on the shoulder of giants." The only reason I've seen farther is because I've stood on the shoulder of giants. And that really means, like, the only reason why we all know of Newton and all his wonderful accomplishments is that he's built on the ideas that everybody else has built on. And that's the same with this model of atom. I mean, Bohr wasn't wrong. He just didn't know everything. And he made some great progress from Thomson and Rutherford. And Thomson, although he wasn't right, he's not bad. He deserves a lot of credit for what he did. He moved us further along. And so I think that's why this showing those history of how we've gotten from one wrong model to the most current model of the atom is really important. But now we will focus on the nucleus and what makes up the nucleus. And we're going to see that we're going to talk about the protons, the neutrons, and the electrons. But we're not going to go further, but we can acknowledge that what are electrons made up of? And you get into quarks and other things like that. So we're going to kind of stop at the electron level, and we're not lying to you, but we're not also overcomplicating it, because knowing the electrons and how they work can describe most of the phenomena that we need to. You should first take a couple seconds to pause the video and look at this chart, because this chart is a good summary of everything you really need to know about that nucleus. Where the different particles are, what's the charge, what's the mass. And so take a second to pause this. All right, what did you notice? Did you notice that the protons and neutrons are together in the nucleus? And the electrons are outside, whether we call them in the probability clouds? And that the protons and neutrons have that same mass? And that's significantly bigger than the mass of the electron. You know, one analogy is, if I ask you to lift up a car and then put it back down, and then I put a water bottle inside that car, and I ask you to lift up that car again, are you really going to notice the difference between those two masses? Probably not. That's the relationship between a proton and an electron. So a car's mass to a water bottle's mass, you can see why we use the idea that an electron has a mass of 0, because it's, for all intents and purposes, it is 0. You'll notice at the bottom we explain a little bit more about the AMUs, or atomic mass units, and that's what we've used to better communicate and talk about the mass of these particles and then eventually the atoms, because it's very hard to understand something that's 1 times 10 to the negative 24th in size. And so instead of talking about that many grams, we call that like 1 AMU. Well, the good news first is you don't have to memorize the data on all these elements. We give you the periodic table, and so you just have to learn how to read that periodic table. So if you look into one of the squares with the element that you are interested in, it will tell you that the atomic number is okay, and they usually give that above the element, either to the left, right, or center. And then they give you the average mass, and that's on the bottom, and it's the average mass. And we call that mass the atomic mass. Sometimes you'll see it as average atomic mass, but if they say atomic mass, that is an average, and we'll talk about that a little bit more in just a second. But the atomic number, that's going to be the number of protons. And so some of the different periodic tables might look differently, but they will always have a key. So if you forget, is 26 the mass or is that the atomic number? Just look on the periodic table for one of those keys. And some periodic tables actually give you more information than that. They might tell you about the density or the state of matter or if it's diatomic. Ours has a lot of good extra information. One of Dalton's ideas, one of the earlier people with the atomic model, he said that all oxygen atoms are the same. And we've now come to realize that no, that is not true. In fact, there's something called isotopes. And isotopes are the same element, but they have some different properties because they vary in how many neutrons there are. And let's think first, why are neutrons so important? Well, protons are positive, and so if you put a bunch of positive things in the middle in a small space, they're going to repel each other, and that's a lot of force of repulsion in that nucleus. So what the neutrons effectively do is they space out those protons and lead to a more stable nucleus. But especially when you get into those bigger elements, you can, which element is stable? It might be okay with 55 neutrons, and it might be okay with 56, but with 57, that's too much, and it leads to an unstable version of it. So the main idea is that these different isotopes have different properties, and it's due to the number of neutrons in the nucleus. And if there's too many or too little, those nucleuses are unstable, and so the element will decay. And if you remember talking about nuclear chemistry, you learned about decay last year. An analogy we like to make is M&Ms. So you have peanut M&Ms and crispy and peanut butter and almond. Well, they all have slightly different properties, but they're all going to be M&Ms, the same element, and they're going to differ in their weights because they have different neutrons. What's inside is a little bit different. So I like M&Ms as a good example for isotopes. So we're going to introduce another vocab word, and it's mass number, and this is different than average atomic mass. And we need this to talk about the same atom, but with different mass, and so those are isotopes. So we use mass number, and it's the addition of the number of neutrons to the number of protons. So if something, for instance, had 5 neutrons and 6 protons, its mass number would be 11. And we use this notation to illustrate the isotope. So often this is called isotope notation because it tells us the mass, and it tells us the number of protons, and then you can use basic math, 4 minus 2, to figure out that there was 2 neutrons, okay? So there's 2 neutrons in this helium atom. Now here's carbon, and you don't have to memorize which atoms have which isotopes. That's not something you'll ever have to know. But carbon has a couple different isotopes, carbon 12, 13, even 14, and there can be different notation. So when it's like this or like this, that dash 12, that dash 13 is the mass number. So that's the same thing as saying carbon 12, or in this case, carbon 13. And often we leave out that number at the bottom. And we leave that out because all carbon is going to have 6 protons. And so it's assumed that you have the periodic table and you could fill that in with 6. So both of these are proper notation for isotopes. They're just, whether you're kind of writing it out in a paper or maybe doing it in a problem, you'll just see it a slightly different way. So although the different atoms can have different versions that we call isotopes, the nucleus of certain versions are going to be more stable than others. And so we're going to be more likely to find that version if we look in nature. So just imagine if you're taking a scoop of carbon, you're going to find one isotope, carbon-12, a lot more often than you're going to find carbon-14. And we call that relative abundance. It's like what percentage of the carbon in our world is carbon-12 versus carbon-14, or hydrogen-1 versus hydrogen-2 and 3. And so we call that relative abundance, and we use that to calculate the average mass. So you can't just take carbon-12 plus carbon-14 divided by 2 and get the average mass, because they have different relative abundances, so they're not as common as each other. So you have to have a weighted average, and this is very similar to how you would calculate your overall grades. So here's your weighted average in school. And so let's say your formative scores are 90, and formatives count for 10. So you're going to take that 90 times 0.10. It's like, how much does it count for? That's what we call the weighted average. And then you're going to take the 80 and you're going to multiply it by its weighting factor. And so you're going to get 9 and 72, and then you add those up. And so the total weighted average is 81. And so you can think about formatives accounted for 9 out of that 81 points, and summatives counted for 72 out of that 81. But don't forget, do your formatives. They still help you improve that summative grade. So we will never make you remember like how abundant a certain isotope is, but usually one will be a lot more common than another. And you can infer based on the average mass which one is going to be the more common one. So let me first use an example. If you had 4 quizzes and you scored a 9, a 9, a 9, and a 10 on it, your average would be 9.25. But let's say for a second we didn't tell you your scores on your quizzes, and I just said you had an average of 9.25, you can probably assume that you scored 9s a lot more often than 10s. And in fact, because you know the decimal is 0.25, you could actually give me a percentage. And so the same thing applies for the average atomic mass of an element. So magnesium has a mass of 24.305. And so it's reasonable to assume that there's 2 isotopes at least of magnesium, and one's going to be a 24 magnesium, and one is going to be Mg25. And which one is going to be more common? Well, the average mass is 24.305, so that's a lot closer. So this one's going to be more common, and again, it's going to be about 70% of them are going to be Mg24 versus 25. So you can use that average to make some reasonable assumptions. To calculate that weighted average atomic mass, you need to just know the mass of the different isotopes, and you need to know the percent abundance, so how common they are. And so what you're going to do is you're going to take the mass and you're going to multiply it by the decimal percent abundances. So you don't multiply it by the percent, but you would multiply it by the decimal. So you move that decimal over 2, and so you have 38.964 times 0.9, and you get that, and you add it to the other isotope to get the average mass. And I would say most elements have like 2, but they could also have 3, 4, 5, even more isotopes. But for the problems we're going to work on, they're going to probably have 2, 3, or 4. So far we talked about isotopes, which are versions of the atom that have a different mass due to the different number of neutrons. Well, there's also things called ions, and ions are the same element, but they have a different number of electrons. And if you remember, electrons do not affect the mass because they have such a negligible mass, but instead they affect the charge. So you can gain electrons, okay, get more negatives and become negatively charged, or you can lose electrons, so you're losing those negatives and become positive. So you have 2 types, you have positives and negative ions. And so normally you assume that the elements on the periodic table have the same amount of electrons as protons, because on the periodic table, how they sit, they are neutral atoms. So certain elements tend to gain electrons or lose them, and metal elements metals, tend to lose their electrons, and so thus they become more positive because they've lost more negatives. And so they're called cations. So Miss Runk put her cat Blaze in this because she loves her cat, so definitely talk to her about that. But I like to show you that you can think of cations, meow, meow, as positive. See, these are my paws. So we're trying to help you with that analogy that cations are positive. On the flip side, nonmetals tend to gain one or more electrons, 1, 2, 3 usually, to become more negative because you're gaining negatives. And so we call this an anion. And although this is a stretch and is not as good as the cation example, it looks like the word onions, and if you smell like an onion, that wouldn't be good for most of us. So anions become negative and cations become positive. Now, that's an introduction to the atom, and we're assuming you knew some of these basics. We went through some of the early scientists, their models, what they show, the more current model, which is the quantum atom, which we'll get into, and then some of the subatomic particles and their properties. So hopefully this made sense. Otherwise, go back and maybe rewatch it and or reach out to your teacher for more questions.